Welcome to This Explainer. Have you ever caught yourself wondering how your computer actually thinks? And I mean really mechanically thinks, down at the silicon level. Well, today we're going to trace the absolutely fascinating journey of how a processor runs code. We're moving step by step from the strict, foundational logic of the RISC V architecture, all the way up to the mind-bending hardware gymnastics of speculation. It's an incredible story of order, chaos, and literal time-traveling hardware. Let's get right into it.
Here's our roadmap for the explainer today. We're going to start with the RISC V foundation, then look at memory and data transfer before decoding instruction formats. From there, we'll hit advanced execution and bottlenecks, and finally, wrap up with hardware speculation and control.
Okay, let's dive straight into Section 1, the RISC V foundation. Basically, the ground rules of the processor.
So to really understand processor execution, we've got to start with the language the processor actually speaks. At its core, RISC V is a simplified foundational instruction set architecture. And what makes it so incredibly beautiful is its modularity. Because it's a reduced instruction set, the core rules are super simple. This allows engineers to take this exact same framework and build everything from a tiny embedded microcontroller running an infinite loop all the way up to a massive, fully fledged supercomputer.
Now think of the processor's immediate loading dock as a workbench made of exactly 32 integer registers, each 64 bits wide. All the arithmetic operations, the actual math, happens right here on these registers. And here's a fun little quirk you should absolutely take away from this. Register X0 is permanently parked at 0. It's read-only. It's hardwired to absolute nothingness. Processors actually use this constant 0 all the time as a super clever shortcut to copy data between other registers.
Now that we know where data sits during active calculations, let's look at Section 2, memory and data transfer, which is essentially our warehouse.
You see, RISC V strictly enforces what we call a load/store architecture. Remember that incredibly fast 32-register workbench we just looked at? Well, those registers are lightning fast, but they really don't hold much. So the processor has to rely on a massive memory warehouse, holding up to 2 to the 64th power bytes of data. That is a huge amount of space. But here's the catch. The processor cannot do math directly on the data sitting in that warehouse. Data has to be explicitly loaded from memory into the registers, processed, and then stored back. It's a constant, highly choreographed dance of importing and exporting.
Now you might be wondering, how is data actually physically arranged in that massive warehouse? When you're storing a multi-byte piece of data, which end goes in first? Well, RISC V standardizes on something called little endian. This basically means the least significant byte, the smallest piece of the data, gets stored at the lowest memory address. It's kind of like writing the number 1024 by putting the 4 down first. I know, it might seem totally backwards to how we read, but standardizing this prevents total data chaos when we're moving information around.
With all that data flowing back and forth, we arrive at Section 3, decoding instruction formats, or as I like to call them, our standardized boxes.
Imagine you're writing a program, and you type out a standard C code calculation just like this one. To us humans, right, it's a simple algebraic sentence requiring a few basic math steps. But to the hardware, this whole thing needs to be translated into bite-sized, standardized, physical tasks.
Think of this mapping right here as our Rosetta Stone. It shows us exactly how that high-level C code is broken down. You see, RISC V instructions are super rigid. An arithmetic instruction like add or sub takes exactly 3 operands, 2 sources and 1 destination. So to solve our equation, the compiler has to break it down into 3 separate RISC V assembly instructions. It adds G and H into a temporary register, adds I and J into another, and finally subtracts those 2 temporary registers to get F. The whole shebang has to conform to these simple 3-part verbs, no exceptions.
Let's see how this builds into the machine code itself by decoding these 32-bit instruction layouts. Now notice how across the different instruction formats, whether it's an R-type for arithmetic or an I-type for loading data, the opcode, which is the bit that tells the processor what action to take, is always placed in the exact same 7-bit slot at the very end. This is definitely not an accident. By keeping the opcode stationary, the hardware can decode what to do instantly without wasting precious clock cycles searching for the command. It is built purely for speed.
Speaking of speed, let's transition from the rules to the physical reality. In Section 4, Advanced Execution and Bottlenecks. Basically, the processor's assembly line.
So here's the absolutely crucial point. How does the hardware keep up with millions of these instructions without stalling out? If one single instruction gets stuck waiting for data to load from our massive memory warehouse, does the whole processor just completely freeze up?
Well, historically, engineers tried to solve this with out-of-order execution frameworks, like Tomasello's algorithm. The idea was pretty straightforward. If instruction A is stuck waiting, let's just skip ahead and calculate instruction B. But they hit some major bottlenecks. The biggest one being the Common Data Bus, or CDB. Think of the CDB as a single, highly congested highway inside the chip. Everything executed out of order has to broadcast its results back onto this single highway, causing massive traffic jams and severe hardware complexity. And worse, when errors happen out of order, it creates imprecise exceptions, which makes it nearly impossible to figure out exactly where the program crashed.
To solve these nasty traffic jams and maintain precision, modern processors pull off the ultimate magic trick. Welcome to Section 5, Hardware Speculation and Control, where we literally guess the future. Instead of just waiting around for the data highway to clear or blindly executing out of order, the processor literally guesses the future. It predicts the results of instructions, like figuring out whether a conditional branch will be taken or not, and just keeps calculating ahead of time based purely on that guess. It is a breathtakingly audacious strategy to keep the processor's pipeline fed and moving.
But to manage this kind of hardware time travel without totally corrupting our precious register workbench, the processor has to follow a strict three-step lifecycle. First, it executes instructions wildly out of order. Second, it traps the results of those speculative calculations in a special holding pen called the reorder buffer. And finally, step 3, it commits those results back into the permanent registers strictly in sequential order, exactly as the programmer originally wrote them.
This reorder buffer, or ROB, acts as the ultimate quality control checkpoint. It provides temporary, hidden registers so the processor can play out its speculative guesses safely. It meticulously tracks the instruction, its intended destination, and the guessed value. And only when the processor is absolutely sure its guess was correct does the ROB finally release the data. This gives us the incredible speed of out-of-order execution paired with the flawless safety of an in-order finish. A real game-changer.
Which leaves us with this final, truly fascinating question to ponder. If processors are constantly guessing the future to run our code at lightning speed, what happens to the system when the guess is wrong? I mean, think about the overhead of flushing out all that incorrect work, rewinding time, and starting completely over. The complex mechanism to check and correct those guesses is essentially the hidden tax we pay for modern computing speed. Just a little something to think about the next time your computer instantly opens an app. Thanks so much for joining me on this explainer, and I'll see you next time.